All right. Hey, everyone. So today we're going to do kind of the second step of circuit analysis. So we've done the first step, which was thinking about how to take a big group of resistors and simplify them down into a single resistor, a single equivalent resistance. And then today what we're going to talk about is what we do after that. And our ultimate goal is to know how much current is moving through each part of our circuit, and then also how much voltage drops across each part of our circuit. So when I say that, what I mean is essentially how much energy does it take for the electrons to do that thing? Because they're going to lose some energy when they do. So working through their way through a resistor or lighting a light or spinning a fan, that takes effort. And so the electrons that are done doing it are going to have less energy, less voltage, less electric potential than the ones that before they did it. We're going to start with some very straightforward circuits, and then I'm going to look at one more complex circuit. I will say that for Physics 9, I will not test you above something that is just series or just parallel for this particular subject. We are going to look at one because I think for a lot of you it'll make sense, and for those of you who are going to AP, that's absolutely something we're going to do. So the broad topic that we're covering today is something called Kirchoff's laws. We've already joked a little bit about how cosmopolitan electricity and magnetism is. We've had Frenchmen and Italians, we've had Americans, we've had Brits, and now we have a Russian. Oh, German, can't forget them. So it's very cosmopolitan practice, especially coming on the heels of the rest of kind of freshman physics where everything is Newton all the time, basically. All right. So Kirchhoff's laws talk to us about how voltage and current are split in different circuits. We're going to look, first of all, at a fairly straightforward circuit, which is just three resistors in series. And we are going to have those three resistors be a 9 ohm resistor, a 6 ohm resistor, and a 3 ohm resistor. And they are going to be hooked up to an 18-volt battery. All right. When we're trying to figure out what is happening with a current or voltage, the very first thing we have to do is actually the last thing we did, which is we need to find an equivalent resistance. So here, pretty straightforward. We're going to do 9 plus 6 plus 3, which last time I checked is 18 ohms, and that is our equivalent resistance here. Now, the reason we do that is because once we have an equivalent resistance, then we have an equivalent resistance, a total voltage, that's the voltage of the battery, and that means that we have 2/3 of Ohm's law, which means that we can solve for the other one. So we're going to plug those into Ohm's law. We have 18 equals I times 18. And we end up with a current of 1 amp. So the reason that we start with finding an equivalent resistance is that it allows us right after that to find a total amount of current coming out of the battery, which is 1 amp. 1 coulomb of charge each second comes out of that battery. And so now we get to start thinking about where it goes. And in series, current really is the place that we should start because it turns out the current doesn't really have any choices. All 1 amp has to turn that corner. All 1 amp has to come through the first resistor and the second and the third and then it comes back and goes back into the battery. So if we are in series, then we are going to know that the current through the first, so, and this is in series only, that the current through the first device and the second device and the third device are all equal, and they're equal to the total amount of current coming out of the battery. Now, if we look at that, what we are going to see is that for each resistor now, we also have 2/3 of Ohm's law. So we have a current and a resistance, which means we could actually multiply them to get a voltage. And that works. And that's one of the really cool things about Ohm's law. I mean, most of us were able to intuit the actual relationship of Ohm's law, that, more resistance lowers current, that more voltage increases current. But the really cool thing to me about Ohm's law is it doesn't just work on the big circuit scale, it actually works for each individual resistor or fan or light in a circuit. So here, the voltage is going to be current times resistance, 1 times 9, 9 volts, 1 times 6, 6 volts, and 1 times 3, 3 volts. Now let's think a little bit about what that really means, because I think a lot of people, this is where it gets a little fuzzy. If we're thinking of voltage as like a form of potential energy, which it is, right? Thinking about our mountain stream where we go up the mountain stream, that's our battery. It gives us 18 volts of energy. And then we're going to come down, right? And we're going to come down in a couple little drops. So the first drop happens here. And it's where we lose 9 volts of that energy. And then we have a second drop that happens here. We lose 6 more volts of energy. And then finally we have our third drop right here, and we lose 3 volts of energy. And now we're back down to ground level. And by the way, ground level is actually a phrase we use in electricity to talk about an electron that has lost all of its energy. So that is exactly what we're seeing in this circuit. The battery boosts it up to a higher potential energy, but as it does work in the system, whether that's going through a resistor that just makes it hard to get through, lighting a light, spinning a fan, it's going to lose and lose and lose until it's back down at the ground and ready to go back into the battery. And in fact, that's what a short circuit is. A short circuit is when it doesn't get a chance to lose its energy before it goes back into the battery. And that's why it causes like super hot battery. You can cause a fire that way, because the electrons are getting like re-energized and re-energized and re-energized, but never losing any energy. All right. Now, something you'll notice, 9 plus 6 plus 3, well, that equals 18. And so, again, in series, the total voltage that those electrons were given is going to equal the sum of all of the energy they lost, okay? So in this case, they have, in this case, they've been given 18 volts. They need to lose 18 volts. Well, they lost 9 and then 6 and then 3. So we've lost all 18 volts. All right. Let's think about a parallel. Let's have 8 ohm and a 6 ohm. We're going to have a 12-volt battery. All right. First step is the same. We're going to have to find the equivalent resistance. So here, 1 over R equals 1 over 3 plus 1 over 6. Okay, that's 2 over 6 plus, or sorry, yes, 2 over 6 plus 1 over 6. So that's 3 over 6, which means that the equivalent resistance is 6 over 3 or 2 ohms. Great. Second step, we're going to still find the total current coming out of the battery. So V equals I R. Okay. Current here is going to be 6 amps. All right. Things change when we're in parallel. When we were in series, we started with the current and then figured out the voltage. We're going to do the opposite in parallel, because in parallel, we actually have this split that happens of the current, right? So the current can either go top or bottom. And for now, we don't really have any idea of how much is going to go to the top and how much is going to go to the bottom. Some of you may have some inklings that you know, and you probably do. We'll come back to that here at the end. But what I do know is that no matter which way I go, whether it is top or bottom, the electrons have to lose the same amount of energy. Because when they come back together, they need to have the same amount of energy to go safely back into the battery. They need to be at ground state. So, what's going to happen? We're going to have, whether it's on top or on bottom, it needs to lose 12 volts of energy. So, in other words, here, for each of those things in the series, and we only have 2 here, but it would be true for 3 or 4 or 5 or 8 or 20, each of them has to drop 12 volts. And so that is different, right? That is different from what we saw before, where all the voltages add up in series. Here, it actually acts more like what the current did before. And so that's what we start with in parallel. We start with that statement about voltage. Now, what do we have? We have 2/3 of Ohm's law on each of those branches. Voltage and resistance, and we can find current. So that would be current is voltage divided by resistance. So 12 divided by 3 is 4 amps up here. 12 divided by 6 is 2 amps down here. And what do I notice? I notice that 4 plus 2 adds up to 6 amps, which was my total amount of current. So again, the current here is acting more like the voltage from before. And so now, whether we have something in series or in parallel, we are able to find exactly what happens to the current and the voltage. Now, some of you may have thought, you know, this bottom branch is twice as hard as the top branch to get through. We could use our analogy of stop lights, and it takes twice as long to get home. Maybe that means that half as many cars are going to do it. And it does, right? Twice as much current, half as much current. So, proportions do work. I will tell you the reason that we learn Kirchoff's laws, though, is that when it is 8 or 20 or 120 different resistors, suddenly proportions don't look that appealing, right? So if it's just 2 or 3, it can be helpful. It's definitely helpful to know that equal resistors will have equal amounts of current in a parallel. Um, Equal resistors will have equal amounts of voltage in a series. Those are all really helpful things to know. All right. I like to organize Kirchhoff's laws in kind of a table. So thinking of it as um, in series versus in parallel, and what happens to the voltage, what happens to the current. All right. In series, and let me adjust this a little bit. In series, we know that all of the current that comes out goes through the first one and the second one, and so on and so forth. And we also know that this is the best place for us to start when we have a problem with series. And then what do we end up seeing afterwards? We end up seeing that all of those voltages just need to add up to the total voltage drop. Parallel is the opposite, right? So the total voltage drop in parallel is the same as is dropped in each of those branches, because no matter which branch the electron takes, it has to lose the same amount of energy. And then the total current, it splits, right? It's in multiple different branches, and so we just need those branches to add up. And where is the best place to start? The best place to start is here. All right. I'm going to do a separate video where I tackle a more advanced Kirchhoff's laws problem. Again, if you're in my physics class, that's not something that I'm going to test you on. As long as you would be able to do something straightforward like one of these, we're good to go. But if you're interested, or if you are somebody who does not have me as your teacher in the classroom, and you want to look at a Kirchhoff's laws problem that is a little bit more advanced, then join me on the next video. Thanks. Bye.